with that, thank you everyone for coming. We're going to go ahead and get started with demo day. So up on deck, we've got Florian going first with recent Dask DataFrame improvements. And then after Florian, Matt will talk about large-scale population of vector databases for RAG. And then last up, I'll talk about easy GPU debugging. And we'll see if we have time. Maybe we'll have an impromptu, someone else gets on the stage. But with that, I'll hand it over to Florian.
All right, so yeah, as James said, I'm going to talk about recent improvements around Dask DataFrame. So there have been actually a couple of changes that are pretty relevant, like P2P shuffling has been released a couple of months ago already. I think 2 weeks ago, we released the query planning by default. That also came with a new Parquet reader and a couple of other, say, quality of life and performance changes, and all bundled together is actually a very new experience for users of Dask DataFrame, and I'm planning to show you a little bit of this. But first, let's look at what the legacy DataFrame can. So for the record, if you are updating to the newest Dask version, you can still opt out. I don't recommend it, but if for whatever reason you want to set this config value, please, before the import, and you're ready to go. We'll basically use this as a baseline and see what kind of data I'm going to show you, what kind of query I'm going to run, and then we will look at the newer version. Now, this is using TPCH data. TPCH is a I think industry standard benchmarking suite. So I'm looking here at, say, the line item table. So that's a transactional data of orders, items, quantities, shipping instructions, etc. So what one might ask of this data is a, say, typical business query, like give me the average quantity of a certain return type thing with a couple of filters like that one. So that's easy to express in Dask. As I said, this is the traditional legacy data frame, and I can compute this. That's so far so good. You see a lot of stuff happening on the right-hand side. For the record, this is, I think, this is actually not that much data. This is now 100, the TPCH 100 scale. This is about 100 GB of data. So this is running through in a couple of seconds for this demo. So 10 seconds, that's not too bad. For this, say, very simple thing, if we want to look at a little bit more sophisticated thing, like this is one of the standardized TPCH queries, number 3. If you speak SQL, there's the SQL. I don't really like SQL, so let's look at the data frame. We read Parquet, 3 tables. We apply a couple of filters. We join tables, and in the end, we are selecting a couple of columns, sorting, etc. So this is an actual, well, complex query, and we can run this now. And this takes a little bit of time. So apologies, this will run for about a minute, but embrace the pain. I'm sure you are used to this kind of thing. This will run, it will finish eventually, but it's not a really pleasant experience. And this is why reasons for this are actually, there are many reasons, like this final selection of columns cannot or is only actually evaluated at the very last. So in the legacy data frame, we take whatever you wrote down literally in the order you are providing it without any modification. And this, well, it works, but it's not necessarily slow because it's not necessarily fast, because we have to load a lot of data that we actually don't really need. So we will just let this finish. It will finish in a couple of seconds, and then we will jump over to the new data frame backend that is now shipping by default. So that took about a minute, and we have, I don't know, 10 lines that is answering whatever this query is asking of us. Now let's look at the same, basically, notebook, but we are using the default, so we are not setting any config values. We can actually use the same cluster. We look at the same data. Again, the very simple query at first. This will require minutes to restart. Now, here we are. Like now, this query, this Dask DataFrame or Dask series in this case, and you already might notice that there is a thing at the bottom. This thing is what we call an expression, and this is essentially the meaning of whatever query you typed. And you can look at this like there's a pretty print function which breaks this up in a tree a little. So this is still pretty complex, but this is what you wrote down. So there's a filter. Now projections, we calculate the mean value, and we read a bit of Parquet. Now the interesting bit here is we can call optimize on this. And this is then taking your expression and is rearranging it in a way that is typically much faster. Now what we can do here, or what we can see here, is that a lot of these, say, filters and projections actually vanished, and this read Parquet thing got a little bit more complex. And just for readability purposes, let's look at this again. Path, columns. So what this is doing, it is pushing down filters and columns to the very I/O layer. And this gives us the opportunity to read the Parquet file or read only sections of the Parquet file that are actually necessary, without you having to provide this to the actual read Parquet call yourself. In the legacy DataFrame implementation, you could have done basically read Parquet and provide this as keyword arguments. This is, of course, only a couple of the optimizations we're actually performing here, but this is probably the easiest to grasp. So this query took about 10 seconds the last time, should be a little bit faster now. Again, this is a very simple query, so the performance gains expected here are also, say, relatively slim, but it's already about twice as fast, a little bit more than that. If we look, and yes, and we have something I really like, which is what we call analyze. So whoever had already problems with partition sizing, for instance, this is now giving you some statistics about, say, what kind of partitions you have at what stage. So this is great for debugging. I really love this feature, so I wanted to show this. Like you can see that after the group by, you have really tiny partitions, which is kind of expected, right? It's a reduction. I'll show you the same thing for the query 3 later. So we can do the same thing again. I will print the optimized query plan. Oh, and this is, of course, very complex. But looking into this, there are joins. And here's, for instance, a Parquet read call, again with filters, again with a column projection. So, for instance, from this customer table, we are only reading a single column, even though we didn't specify anything special here. But just by interpreting this query plan, we know that's the only column we are actually interested in. So this is what comes out of it. So running this again should be much faster now. So again, the last one ran for a minute. I don't really know how long this will take, but as you can see, it's almost done. Yeah, so that was 20 seconds. Again, more than a factor of 2 better here. I'm also running the analyze, and we can look through a more complex example in a minute here, where I can also, say, motivate a little bit of future work. While we're waiting, or no, not while we're waiting, we actually have to wait. Yeah, let's look at the analyze plan. Like there are a lot of stages. So right, this is heavy debugging. But as you can see, it's actually straightforward. We are reading Parquet data sets, we are joining it, and we can already see. So this starts with about 700,000 rows. On the left-hand side, we have 30,000 rows. 150 remain after the join. So this is an inner join that reduces data. With 3 megabytes of partitions, that's actually a little bit small for our taste. I think Dask typically shoots for something like 50 megabytes for a partition, depending on the circumstances. And this is actually an angle where we are hoping also to improve in the future to make this a little bit automated, like rechunking this again. But yeah, continuing this, we are actually trying a very big table with 1 million rows, 10,000 are left. So you can walk through this and see, is there anything we can optimize here? I really like this. For the record, and this is basically an end-to-end view on what, say, as I said, we have a couple of different optimizations and improvements over the last couple of months. If we compare the, say, legacy data frame of a year ago, maybe 18 months ago, without any pandas improvements we did for Dask, without any pre-planning, without new Parquet reader. This is query-free. So this is actually on a terabyte scale, on a bigger cluster, because otherwise it would fail. The old, say, ancient DataFrame would run for, well, let's say 20, 25 minutes. The new one runs for 50 seconds. So this is a factor of 20 of improvement compared to what was once the Dask DataFrame to what it is right now. And this is now the default for everyone. And it's been released in version 24.3.0, I think. There have been a couple of patch releases since. We haven't encountered any major bugs yet, but we are, as soon as we are encountering something, we are trying to push out something very quickly. So if you encounter any issues during migration, please let us know. It's intended to be just a drop-in replacement. Pip or conda update Dask and red EUR. If this is for whatever reason not as smooth for you, please let us know, and we want to fix that if that's possible, of course. Right. So this is everything I have prepared. If there are any questions, I'm happy to answer them right now.
Florian, briefly, can you say a bit more about the image you're showing? You showed that the top bar was the old data frame, the bottom bar was new data frame. What are the different rows? What do they mean? Yeah,
right. So the very first row is a very long time ago. I think this is running Pandas 1.5. It's using the task-based shuffle system. And then every row introduces a new upgrade. Like the first row uses Pandas 2, very minor change. The next row is introducing string data types. So many people might have noticed that we have this convert string option now. For a couple of people, this caused some pain. We are addressing this. We are working on that. But that's the gain we are seeing, that say previous objects. So previously strings were treated as objects in NumPy land. Now they are using PyArrow string data types. And this, so I'm not showing memory usage here, but memory usage dropped here significantly as well. Actually, the first two rows had to run on twice as large instances to just finish. And then as we continue, the number 3 was P2P shuffling. So that was a new, better scalable shuffle algorithm. We got some fixes in Pandas in about, say, removing GIL contention and copy on write. For this specific query, though, it's actually backfired a little, or I messed up during my configuration. But then 6th row query planning, this is what I showed you just now. And last but not least, we also got a new Parquet reader in, which looks very, well, almost unimportant when we look at this scale. But of course, this is again improvement of 20-30% in speed. A full set of TPCH measurements are about to release. We are currently working on this, polishing it a little, but in the next couple of weeks, we have more data like this out in form of blog posts and such things.
Thanks, Florian. Any other questions that folks might have for Florian? Awesome. Okay. Thanks, Florian. Really appreciate the presentation. That's exciting stuff. Okay. Next up, we've got Matt talking about vector databases for RAG.
You're muted, Matt.
Yeah, that's right. Yeah, let's go share my screen. This will be a far less polished demo. So thank you for the excellent work.
Mine will be too, just as it's going to get decreasingly less polished, increasingly less polished.
Yeah. My demo doesn't even work. So like I was playing another thing. Ben, a couple months ago, played with RAG using Llama Index and Dask, and showing how it's easy to sort of use Dask parallelism with RAG. RAG is like a very easy parallel process. Brief context, when using an LLM like ChatGPT, there's some challenges. It's only trained on public data that was like a year old. And so often you want to augment an LLM with more recent data. A common way to do that is to put a bunch of documents and say, hey, LLM, here's like all of the documents you should look at. It can't look through all of them, and so you want to put them in like an easy to query way. a good way to make a bunch of documents easy to query is with a vector database. So there's this common pairing today of vector databases and LLMs, which comes with the name RAG, which people seem to like much. I wanted to make a good example of using RAG with Dask on a large data set. I was playing with Archive. This is 3 or 4 terabytes of scientific articles sitting in the cloud. And so the first thing you do with RAG is you want to like create a bunch of documents. So for each tar file in this list of 7,000 tar files of PDFs, I look through each PDF file, and for each PDF file, I pull out each page, and that becomes a document. And let's just go look at what that looks like. So here is here's a list of file names and page text pairs. This one is looking at the Galilean Lie model of delta function potential. I don't know what that means. Some quantum physics thing written in 1999. Turn to a data frame. And then the next thing we need to do is we need to compute an embedding for each of those things. So Ben was playing with this using this package called llama index, which is, I found fairly complicated. I was talking to people and I'm like, oh, actually, it's like overly complicated. You can do all this pretty manually. And so I just wanted to do all of it just with like pandas and PyTorch and not with anything more sophisticated. So here's a pretty simple model that does a vector embedding of text. I'm getting it from Hugging Face as a package that has a bunch of models, getting it from there. And I'm just going to like take my text column in my pandas data frame and compute a bunch of embeddings on it. And then let's go look at it again. So great. I've taken each bit of text and I've like let some PyTorch magic code walk over it and compute some vector embeddings. Maybe when you were in a computer science class at some point, you did like count vectorization of documents. That would be a very simple vector embedding. This is a more sophisticated vector embedding. So that's like most we have to do. We need to like take documents, run some PyTorch code on them, get a vector. Then we can shove that into a vector database. I was playing with the vector database LanceDB, which is pretty easy. You can just like give it pandas data frames and it will just like import them into the database. I've already done that. And so I'm now going to search a sort of a very small subset of documents for the text black holes are cold. And that vector database then gives us pieces of information that it thinks might be relevant for that text. And here's an article from George Mason University onto accretion flows in black holes. And I'll bet somewhere in here it talks about temperature, is my guess. There's a few of these things. So these are now the like documents they would hand to your LLM in order to make that LLM have more context. Here for scientific stuff, you can imagine like taking all the Google Docs in your company's Google Drive and like giving the LLM those documents instead. Hey, what is the current healthcare plan that I should use? So the next thing to do is to run all this at scale. LanceDB runs on Amazon S3, so I connect up to an Amazon S3 bucket, and I create a table there, and then I just make a function which, for every directory of tar files, does all the steps I just mentioned, and then shoves it into my vector database. I need to be a little bit careful with concurrent writes, so I'm going to use a lock. I'm going to use a Dask lock to handle distributed concurrent locking. We had a bunch of GPU machines. Everything worked, kind of. I actually used both GPU and CPU. For this particular model, CPU was a little bit cheaper, but that ran. It was kind of weird, though. I think like a thing for us to think about. The reason why I'm not running this live because like it fails a bunch. There's 7,000 directories and like 500 of the times, there's like some weird region misconfiguration. 3 times, like it receives some weird error. I've been playing a lot with like Rust libraries recently, this Delta RS, some arrow things, and like the Amazon credentials in Rust libraries do not seem to be as robust as Boto. Like I used to hate Boto with a passion, but like it does just work in a way that some of these new libraries don't. Yeah, anyway, it's a bit strange. So things are a bit strange, but there is today, I'm gonna move down here a little bit. There is today actually just like an open bucket with thousands and or I guess millions of PDF scientific articles in there. And we can now go and query that. And so it's gonna, oh, I need to, this is dumb. I'm like telling LanceDB the region is US West 2, but I need to tell it again with an environment variable. And then it works. And so now we can go things, we can query, black holes are blue or whatever. And we can go and do a search. Takes a little while, but now we need to like couple this with some sort of interaction piece, like a little chatbot. Anyway, we've like taken all of archive and like shoved, I don't know, 90% of it, the fraction that didn't fail. We've shoved it into this vector database that's like globally accessible on S3. And so, so here's actually a case where the first document was talking about ultra cold cases of non-rotating, that's got to be black holes. But like, we're getting much better documents now about cold black holes than we were getting previously. So all of this is available in this discussion if you want to take a look. Folks from Quantsite have been helpful in interacting. There's like various notebooks people can go play with. So that's it. It's kind of a shitty demo because like there's not an interactive fun thing to do. Most of that's because like there's a bunch of weird stuff happening sometimes with Amazon S3 and these various Rust libraries. That's it. Sorry, I guess maybe a couple of points. One, it was fun doing RAG without any technology. It was just like basic Python code, pandas, and like applying some PyTorch model onto a pandas series. And it was nice to demystify a little bit some of this like interesting hot topic. There's like a lot of libraries made like a lot of fun stuff around this thing, but like actually it's a lot of complexity you don't really need. And it was fun to make things in a very basic way. Two, it was kind of cool running all that at scale. It's the normal like Dask coiled pitch. Three, I'm kind of griping about LanceDB and the weird things that it seems to require. But I do kind of like that there's just this like, it's all just like an S3 bucket. And it's not like a Postgres database I have to share access to. Like anyone can go look at this. And that's really cool. I really like that architecture. And then four, it would be nice if we could smooth out some of the rough edges between Python, Cloud, and some of these other libraries. There's a lot of roughness here. So that's it. Those are the basic messages. End of demo.
Awesome. Thanks, Matt. Do folks have any questions or comments for Matt? I've got one. So yeah, let's say we go ahead and smooth out all those rough edges, and now we like to live in that world where everything is smooth. What is like the cool, fun, interactive demo here that you said is currently missing?
Yeah, so here I'm like asking about black holes being cold. You can imagine going to ChatGPT and asking ChatGPT like, hey, tell me about black holes or whatever. And like maybe ChatGPT has already looked at all of these articles, maybe not. But we can also say, hey, ChatGPT, go look at this database of just archive. And like summarize for me the current state of research on cold black holes. And it could then give you like a much more in-depth response. It can also tell you like exactly which articles it's referring to. Like, hey, these are the articles that I'm looking at to give these responses. This is the text that I'm giving you that I found in order to tell you those things. So we could make a like little chatbot system around it. And that's really common. If you look for like chatbot LLM, you'll find, I don't know, like Streamlit, I'm sure has an LLM chatbot. Yeah. And I'm sure that it's super slick and looks really nice. I've never seen this before, but like I'm confident it's going to look pretty. Yeah, here. So like we could do this. Yeah, so like this is fine, but like the information we got before was better. And then really what we want is we want other people to see this and say like, oh, I happen to have 3 terabytes of documents that I care about. It's actually the process we just saw here is pretty easy. I can go do that myself, but instead of like a public bucket, I'll put it like in a bucket inside of my own company. And now suddenly we've got this like serverless runs inside of a web terminal um, document enhanced LLM system. I don't know, if I was an insurance company, I might want to check every insurance claim that exists. If I was the US federal government, sure, there are many terabytes of federal laws I might want to look at. And I could have here on the side, like also like a little list of like exactly the documents that were relevant for the query. So if I wanted to go and sort of look at them. Sorry, that was a long answer.
Cool.
Good point.
No, yeah, it was a good answer. That's neat. I actually happen to know people at insurance companies who are doing that exact same thing. So this does sound like a nice real world application too. Cool.
Yeah, RAG is like a
Any other?
popular. There are like many
Yeah.
startups right now, I'm sure, doing RAG stuff and trying to get lots of money. Maybe I shouldn't. Like, it's a pretty simple process. I figured it out without knowing much pretty easily. Which is not doing here.
There you go. Awesome. Okay. Well, thanks for showing that. Any other, just real quick before I go, any other questions for Matt? Okay. Well, if not, I will share my screen. All right. Hopefully you're seeing a terminal right now. And hopefully the text is big enough for people because I'm going to be just kind of staying in terminal the whole time. So what I wanted to talk about was a fun experience I had. I can't remember if it was last week or the week before. So I work on Dask, and as you probably all know, Dask runs on lots of different types of hardware, including GPUs. So we can have like GPU accelerated Dask. The problem I have as sort of a Dask maintainer is I'm not really, like historically, I've not been able to help with running Dask on GPUs because I don't have one locally. I often end up just pinging other Dask maintainers, colleagues who actually happen to all work at NVIDIA and have easy access to GPUs. So it's always felt a little inaccessible to me. Last week or the week before, someone opened up a GPU issue, and actually it was a nice marriage of sort of using Dask on GPUs and some recent work that I want to show that's been going on at Coiled to make GPUs sort of accessible. So like me as a Dask maintainer wanting to help on GPUs is sort of the motivation here, but actually, as you'll see, I think this is more broadly applicable to anyone who wants to run code on GPUs. So sort of the easiest way I know for myself to get a GPU, just like be sort of dropped into a GPU machine, is to use Coiled. So I can do Coiled run GPU, and at this point I can do interactive bash. That last part is sort of kind of optional, but if I do that, what'll happen is Coiled will start provisioning a GPU instance for me on the cloud, on my cloud provider. I'm set up right now with AWS, so this will spin up some GPU instance on AWS for me. Right now it's queued. You'll see then it'll start downloading a bunch of software. It's replicating my local software environment, and it'll drop me there on this particular instance. Sort of, this is a short demo here. So I'm going to actually, this whole process takes a couple minutes. So to avoid that couple minutes of silence, I'm actually going to go over to this terminal window here. And this is the results of that command. After this over here is done, it will drop me here. And now I'm connected, locally from my laptop. I'm now connected to a machine on the cloud. It has, what is it, NVIDIA SMI. It has a GPU sitting here. So in this particular case, I've got a Tesla T4 GPU sitting here. And this is like fun. I can do things that I would normally do on my local machine, on my laptop. I can like pip install things. I can Mamba install things. Like the fun thing here is I can maybe, install things that require a GPU to be installed, but I actually couldn't do this on my laptop before. And the fun thing is I can now because I can just easily get dropped onto a GPU VM. I can drop into IPython if I like, and play with PyTorch, for example. So one nice thing is I don't actually have to do those pip and mamba installs because Coiled has automatically synced my local software environment. Back here on my laptop, I actually have just pip installed Torch, Torch Vision, and IPython. And we can see that, PyTorch, Torch Vision have all been installed on this VM. I didn't really have to think about software here, which was nice. But like the really nice thing is not only did it install PyTorch and Torch Vision, it actually installed all of the, GPU bits up here that were needed to make those libraries take advantage of GPU. So now I can actually use PyTorch on GPU accelerated hardware, which is fun. So for example, I have this, I made a Python file here that has some simple PyTorch code. It trains a neural, there are some emojis. It trains a neural network. The important thing here is that it requires a GPU. This line of code here will fail on my laptop because on my MacBook, because I don't have a GPU, I don't have CUDA, all that good stuff, but it'll run here. And then ultimately it'll end up saving, it'll train some file or some model on, in this case, CFAR10 data, and it'll actually save that model to a local file here. So if I now run this file, I actually ran this ahead of time to skip the data downloading step. That's why it's saying the data file is already downloaded. So like right now, if I had actually had another terminal window open, I could like look at the GPU and see that the GPU is being utilized here from this PyTorch model. And we'll sit here and wait a second for the model to train, and then we'll see that we have the model file saved here. And this is exciting because again, this is like something I haven't really been able to do easily before. So just like I can do all the things I can do on my normal laptop here, going back to the context of maintaining Dask, I was able to then like git clone Dask and like check out the right branch and like install the like CUDA driver that happened to be problematic for this issue this person opened up and reproduce the issue that they were seeing. And that was like really useful and just like a delightful experience for me, having not been able to do that before. So if I then just like look at the files here, I can see, yep, there's my trained model. It was just saved. So yeah, that's kind of what I wanted to show. This was just like a pleasant experience for me. So I wanted to share with others to see, see what their thoughts are. I do want to mention really quick that like I'm doing this interactive programming thing here, which is really interesting. I'm just getting dropped into a bash shell. That's really familiar for me, but a lot of people don't necessarily need that interactive experience. They just might have, hey, I have this PyTorch script and I just want you to run it. I don't really want to do anything in the terminal. So for that, you can do something like coiled run. There's a few other knobs here. Like I just did GPU. I just said, give me whatever your default GPU instance is, but you can do, whatever big special, GPU instance you want. Maybe like you're analyzing a bunch of data and you want to be in the right cloud region. And then you can just run, whatever command you want here. And for example, if I had that train.py file locally, I would just run python train.py, and this will do everything I just walked you through sort of interactively. It'll do that automatically for us. It'll spin up that cloud VM with the GPU. It'll make sure it has all your packages synced and the GPU variants as well of those packages. It'll run this script and then it'll shut itself down, which is, it's just like a nice experience. So anyways, that's what I wanted to show. And yeah, do folks have any questions, comments? Okay. If not, then I want to go ahead and thank everyone for demoing today. So thanks, Florian. Thanks, Matt. And yeah, thanks myself. I'll see y'all next month. Have a good one.